right, now we come to 5.4, exponential function. It's differentiation and integration, okay? We look at the nature of the exponential function. Here we go. We have right here, and that is the function that you are very familiar with, which is y equals ln x. And if you graph this guy right here, you can see that x cannot be a negative value, okay? Graph this one, you will see that the function looks right here, and then when x is 1, you got that's right there. The point is 0 when x is 1. This function right here, y equals ln x. For some reason, you want to find the inverse of this function. When you deal with the logarithmic function and to find the value for x, how do you solve for the inverse? There we go. How do you solve for the inverse of the function? Here we go. We take e to both sides, okay? Let's take e to both sides and see what that looks like. Take e to both sides, okay? E to both sides. This is y right here, and this is ln x right here. So there we go. We are now solving for the inverse function, which is solving for x. Technically, that's why you do e to the ln x. This case right here, you have what? E to the y, and this, what's this right here, guys? And that is e to the ln x, which is x itself. Ta-da! You get right there. Now put that back in the form of a function that you usually always do. And that is now y equals ex. There we go. You see it? So this guy is the inverse of the natural log or the logarithmic function. This is where you see the form of exponential function comes from. Graph this one, you will see that it looks like this right here. When I graph this one for you, look, this one, you see that x is 0, you have this 1 right there. So here we go. Again, you can see that the function is, both of them, the graph, they are a graph of two functions and its inverse. They are symmetric over the line y equals x. So there we go. What does that mean? It means this. The inverse function of a natural logarithmic function is called the natural exponential function. Okay, so here we go. Let me state this so you can see in your textbook, and you will see right away. You see y equals, whoa, red ink. We see right here, y equals e to the x. This is if and only if. Okay, guys, this is if and only if. Okay, so, or you can say double F right there. That would do it. Okay, this sign right there, I give you 3 notations. Y equals e to the x if and only if what? X equals ln y. That's it. That is your definition of the natural exponential function. Now we are moving into the properties, just a few properties. It's like, you know, the commandments of exponential properties, and you have to follow them exactly in order to find the true values for certain functions. What properties? Remember, ln in your textbook we have here, ln of e to the x. That gives you what? X. Very good. And what else? And e to the ln x. That also gives you what? X. Okay. These are the properties that are very handy and very, productive when it comes to the logarithmic function and exponential functions to solve for the variables. Let's look at the examples. Okay. I'm going to follow the examples in the book so that you can also, if you miss my lecture here, you can go back to the examples. All right, let's look at examples with me, please. It looks beautiful, right? Here we go. All right, look at the example with me, would you? Okay, here we go. Example 1. Okay, you have right here, you have 7 equals e to the x plus 1. All right. This, remember, this is your, I think, is it Algebra 2 or pre-calculus, the beginning semester of that? For some reason, you want to solve for x. And how do you do that? Well, you have the exponential form, and here you have, so we are using the logarithmic properties. I am going to take what? Natural log both sides, okay? Because I see that's e right there, so it is convenient to take ln both sides. There we go. Okay, you got that? So here we go. Here we go. It is even better to put this in this form right here. There we go. So now, applying the property. What property? I just did with you. Ln e to the x equals what? X itself. Technically, that's ln e. But since ln e is 1, therefore you got is x. There we go. So this one right here is ln 7. That's the left-hand side. And that gives you what? X plus 1 to the ln e. And ln e is technically 1. Can we go home from here? Indeed. X equals ln 7, whatever that is, plug into your calculator and minus 1, solving for x. That's it. Just a reminder how to solve for x in exponential form. All right, I just insulted your intelligence. I'm sorry. Let's look at example 2, shall we? Example 2. Okay, here we go. Example 2, you have right here is ln of 2x minus 5 equals 5. There we go. Now I need to convert this back into the exponential form. The technique, again, what formula am I going to use right here, Mr. Dang? I'm going to give you a good formula. E to the ln x equals what? Shout it out. Correct. X right there. The purpose is to solve for x. So I got my single. I got my x right here. How do I solve for x right here? Oh, I'm going to do what? The same thing to both sides. There we go. Take e to both sides. E to the 5th and e to that right there. Imagine this is another function equivalent to e to the ln u. U could be a function of x, okay? U is a polynomial with the variable x, so that's also u. So your u right here is 2x minus 5. Whatever that is, you got 2x minus 5. And over here, 5. You ask, Mr. Jang, what is 2? I mean, what is e? E, you know, is 2.71 and so on. It's like pi. It is an irrational function. Here we go. How do I solve for x? Well, you know the algebra. Bring negative 5 over. You got 2x equals e to the 5 plus 5. And then the rest is history for you. Over 2. And then plug into your calculator. The book has it. Wow, wow, guys, boy, the book has 3, I have 5, and that's okay too. That's okay. Either way, it's fine. Plug into your calculator, and you have your victory right there. Okay? All right, now let's review properties. Guys, to be fluent in these problems, you have to know your game very well. And how you play your game well? You got to know your rules. What are the rules? Look with me. Look with me. Theorem 5.10. It's a great reminder for you to know these properties, and that's why calculus is a piece of cake. It's easy when you know your rules well. Okay, here we go. Operations with exponential functions. These rules you need to know. It's like, again, I said 10 commandments. You're going to follow that. You will have the truth with you. These are the commandments in exponential functions. Okay, you have, right here, you have a e to the a times e to the b. Okay, what does that look like right here, guys? Let's say a and b both are real numbers. Okay, a and b both are real numbers. Then you multiply the two exponents together with the same base. What do? You keep the base and you add the exponent. Okay, keep the base, add the exponent. Okay, I don't need to give you an example on this one, right? The second one you need to know is to remind you if you have a quotient rule. There we go. E to the a over e to the b. Again, if they both only, look y'all, only they both have the same base, okay? This is the base, and keep the base, and then you take the exponent of the numerator minus the exponent of the denominator, correct? So these are very productive, powerful rules that you can explore, and you can really simplify things that you see in this case. All right, I am moving into the next example so you can see, and that is right now, Mr. Dang, what is e to the x and what is the derivative of that function right there? Okay, this is what we are now going to deal with. We have the derivative of e to the x. What does that look like? Okay, all right, let's look at this, shall we? I'm gonna prove this with you, and then you will tell me how to find e to the x looks like. Okay, here we go. All right, we are interested in what is, I'm doing both notations at the same time. That's, later on it's double derivative, but right now we only deal with first derivative, the order. So what is the derivative of ex look like? Okay, and not just that, how about e to the u? And u is a function of x. What does that look like, Mr. Dang? Well, we'll look at the proof right here. Okay, remember, the equivalent that we have always go to the definition. And what did you have? You have ln e to the x equals what? That's right, ln to the x. This is definition. Okay, that's definition. Remember, when you prove, you always go back to the definition and we look for what we are interested in, and that is e to the x derivative. Okay, now look, this is one line. I'm looking for what is the derivative of e to the x. Remember, guys, remember? ln u derivative, what does that give you? Yep, that's correct. U prime over u. There we go. Same thing. This is definition. It is already, by definition, I mean it is already perfectly set in both equivalent side. Now, whatever I do on one side, I do the same to the other side. Take derivative both sides, shall we? There we go. ln e to the u, e to the x, that's u right there. So you got what? ex what? Derivative over e to the x. That's left side. You see it? That's left side. And what is the derivative of x right here? Correct. I heard someone say that. Here we go. It's like finding the inverse finding the derivative of the inverse. Now, I'm interested in this guy right here, guys. Look, yeah, there we go. Whoa, do you see what I see right there? So I just now simply take this guy over there. So I rewrite that as, okay, here we go. Okay, e to the x, the whole thing, derivative, and then bring over 1 times ex, which is what? Ex itself. Do you see that? Yeah, powerful. Well, we, ladies and gentlemen, we just proved that e to the x, derivative of e to the x is e to the x itself. That's a big check right there. Bingo, bingo. Same thing, equivalent, being applied for e to the u derivative. Can anyone tell me what that is? E to the u derivative, what is that? Yeah, which is e to the u itself. Boom, boom. Now we are ready to do business, okay? Which means that doing examples set you up for your homework, and right now you are playing with big boys. Meaning, guys, I'm sorry, just the function is getting complicated, okay? The exponent is getting complicated, and that is now is a function of x. What does that look like? Let's look at example 3 with me, shall we? All right, here we go. Example 3. You're having fun? I can hear you. Okay, here we go. Example 3. Here we go. All right. We have here is e to the 2x minus 1. That's what I meant. Now you're going to have a big function up there. And what is the derivative of that? Okay, The textbook put d over dx. I put that right there just to save space for us. Okay, you see how space getting too very important for us now? Now look at this. Remember what the formula says. E to the u equals what? E to the u itself. Oh, Mr. Deng being silly. E to the u derivative equals e to the u itself. But what do I do right here? I forgot to give you a very important thing, guys. A very important thing, and that is dangerous. Look, I owe you one thing. Reverse. E to the u times with u prime. Remember that layers right there, and I forgot to give you. Technically, e to the x derivative equals what? Equals e to the x times with x derivative, but that is 1. So that's why you got e to the x itself right there. Okay? On the other hand, remember the layer. Okay? Yeah, the chain rules right here. E to the u, okay? Take derivative of that guy equals e to the u itself times with what? That's right, u prime. Please, I owe you an apology. When the exponent is not a single variable of x, but it is a function of x, then be mindful of another chain rule, the layer, the Shrek thing that we, in that common language. There we go. So here we go. Look at this. Look at this. Your u right here is what? I'm borrowing the concept from integration, but we are dealing with derivative, okay? Let u equals that right there, okay? So now we turn this into e to the u, and you want to do the derivative of that guy. Can anyone shout it out, the answer? Yep, e to the u times what? U prime. Perfect, perfect. Who said that? Okay, here we go. E to the u now, but since the problem asks us to do in x variable, so I plug x back to x minus 1. That's it. And what is u prime? U prime is what? 2x minus 1 derivative. So what do we have over here? E to the 2x minus 1 times with, that's right, 2x derivative is 2. 1 derivative is 0. So the answer here is 2. Bring that out so you will not be confused with another form, 2x minus 1. Okay. All right. I'd like to share with you something else. You can technically do this over here, but let's just keep it this right here. Careful. All right. We'll do that later. That's how you get e to a function of x. You let the whole thing up there equals u. Okay? And then you apply directly the formula right here. Okay? There we go. And then be mindful of another layer, chain rule right here. That's your answer of e to the 2x minus 1, the whole thing derivative, that right there. Okay, shall we do b together? Okay, all right. Let's do b together, shall we? Okay, here we go. On b, you have right here, find the derivative of e to the negative 3 over x. Okay, your exponent now is getting more ugly. What is now, we're looking for the derivative of this guy. That's okay. It's okay, just one step at a time. We let u equals what? Correct. U equals negative 3 over x. There we go. Business is done. We know that e to the u derivative equals e to the u times u prime. There we go. All you do is just take derivative of that guy right there, negative 3 over x. Let's go. What is u prime? Okay, which is right here. You see it? Go. Rewrite this guy if you want to, you don't like doing the quotient rules. There we go. U equals, look, I rewrite that guy. Agree? So technically, right here, look, derivative of u. What is that? U prime equals what? Negative 3, constant, keep it out there. Look, y'all, look. Negative 1 times x, negative 1 minus 1 give you what? Okay, negative give you positive 3, and then x what? Negative 2, but then what? You keep it positive 3 over x squared. All right, okay, remember that, okay, y'all? So you have u prime right here already, u prime right there. That's your u prime. Technically, just plug it in. E to the negative 3 over x derivative. I know I am insulting your intelligence right here. E to the negative 3 over x. There we go. Rewrite that times with u prime. What's your u prime? Right here. That's your u prime right there. And that is 3 over x squared. All right. We want to put this up front so you have a nice form for you. And that is 3 e to the negative 3 over x squared. Ladies and gentlemen, we got it. We got it. All right. There we go. Let's look at example 4. Okay. Example 4, we are dealing with a product rule in derivative. Hope you remember. Can anyone shout out what is the product rule of derivative? U times V. Good. That's right. U times V derivative is U prime V plus V prime U. Perfect. Perfect. Here we have, well, the text doesn't just ask us to just do, simply derivative, but they ask for something else. Find the relative extrema. Wow. You see right now, you know the math, but how do you apply it? Find the relative extrema, which is, remember the function when it has what? It has the maximum or the minimum value, okay? So what function? Here's the function. Function right here is x to the ex. All right, okay. What does that look like? I mean, you can see. Graph it, you can see it, but really it's hard to see the relative maximum until you do derivative manually, which is by hand. Let's do it. There we go. F prime of x. Product rule, gentlemen, ladies and gentlemen. Here we have. All right, there we go. There, this is your u is x, your v is e to the x. Directly do it. What you got? Derivative of this guy, this is the product rule. Okay, guys, there we go. U prime, x prime is 1 times with e to the x plus v prime, e to the x, which is e to the x itself, because that derivative right here. So e to the x time with what? U is x. Perfect. There we go. Now we have what? We have right here, guys, we have right here, which is e to the x plus e to the x times, okay, x right here. I want to be nice to my math form. Can I factor? Look, this one has ex, is x. So ex 1 plus x. In a moment, you see, why do I need to factor out? Because by factoring that out, I have a good observation. Look at this right here. F prime, I need to find what? Look, I need to find the guy right here. That's it. Solving it is not the end. I mean, it's not the what they ask for. Solving it, and what does that mean? You now analyze the problem, and that is, look, what is the relative extrema? Look, extension extrema. Okay, which means, how do I know the function has a relative minimum, maximum, and things like that? Look at this guy right here. This is your what? First derivative. Set that equals 0. Set that equals 0, then you will find, set this equals here. There we go. Y, first derivative, when you set that equals 0, you will find what is what? That's right, critical values. I hope you guys said that. Critical values will give you the position where the function will either increases or decreases. Since this guy right here, there is, oh, Mr. Dan, thank you. Somebody said that. Thank you. Points for you. Okay. Since I don't know boys or girls, I would say point for you. E to the x right here, 1 plus x, right? This guy, can you find any value of that? This guy can be 0. Good luck to that. Nope. E to the x, you cannot. You cannot find any value that x can be, x has that make ex to 0. No, either you get close to 0, but not 0. So the only thing you have left to turn this guy true to the function equals 0 is x equals what? -1. There we go. X is -1. Here we go. You see that this guy right here, we know that the function at this critical values, the function will be minimum or maximum. Okay, but you don't know which one. Remember guys, we do the timetable. You plug in the value of x and and y and then y prime, and then if the function from increasing to decreasing, you got maximum, and then from decreasing to increasing, you got minimum. I want you to see that when you plug into the -1 right here, look at this guys, look. When you plug into the function, and you will see, plug into the function, you will see it will change its sign like this. There we go. So, my bad. So there we go. Okay, so it is something like this right here. Okay, so that point right there, you can see, since the graph, when you plug in and you plug into the f prime, you will see that it is moving from what? From decreasing to increasing. Therefore, this point right here is called, it is relative minimum. It is a relative minimum. Okay, just a review for that. Now, I think we answer that, okay, using the first derivative and set the derivative equals 0. Only one value for x that satisfies the derivative equals 0, which is -1. And then using your timetable, and then you will see at that point right there, it is surely a relative minimum, because the function is what? Moving from decreasing to, that's right, it is from increasing to decreasing, that point right there. Okay, can I move into example 5 with you? Example 5 is a hot potato. Okay, it's a big and hot potato, which is a very good application as well. Okay, here we go. Example 5. Oops. Okay, here we go. Example 5. In a moment, we'll go into integration soon. Here we go. Example 5 you have right here is show the standard normal probability density function. This is, you guys, when you enjoy probability and statistics, you will see such graph like this. Deal with sigma 2 over square root of 2 pi. Notice pi is inside the radical form. E to the negative x squared over 2. All right. They want you to show what? To show that this function has a point of inflection, x equals what? Positive -1. There we go. They want you to show that the function has what? Points of inflection. Okay. All right. How do we solve this function and show that this function has 2 points of inflection right here? Well, what does that communicate to you when you have points of inflection? What's the first thought comes to your mind when you hear the phrase points of inflection? Correct. You don't just deal with one, or you don't just deal with first derivative. You deal with second derivative, which makes the problem more yummy. Let's go, shall we? Let's take first derivative, okay? All right. This one is constant. Leave it there. 2 pi. Ha, you see? The second one is, that's what I'm dealing with right here, okay? This is right here. So let's e to the negative x squared over 2. Ha, you see that? This one is derivative. Okay, all right, one step at a time. I'm bringing it out here for you, okay? Let u equals what, guys? U equals what? There we go. Let u equals negative x squared over 2. That's it. That is it. What is u prime? Well, Mr. Dang, it's simple. It looks, look, the problem looks kind of strange, but it doesn't mean it's hard. You see, just one step at a time. Here we go. Take derivative of this guy. What is it? 2. That's right. 2 times x over 2. Ha! What is that? Negative x. Boom, boom, boom. So we have right here, right? We got right now. So technically, the job is, pretty much done. Because this one, first derivative give you 1 over that pi right there. Time with what? E to the u is e to the u. Time with u prime. There we go. I'll put it out here. It's fine. All right. One step at a time, shall we? Okay, so rewrite this, you will have what? 1 over 2 pi. Put back the value, the variable x, okay? Negative x squared over 2 times with, excellent, negative x. Boom. All right, that's the first news. That's the first good news. We do the second derivative, shall we? Okay, can I erase the word? You can take a picture or you can pause the video and capture my beautiful handwriting. Here we go. Where are we going, guys? We are showing that this function has 2 points of inflection at negative and positive 1. Well, point of inflection requires what? Second derivative, correct. We are doing second derivative. Here we go. All right. With the second derivative builds on top of the first derivative, which is taken another one. There we go. There we go. So you have right here 1 over square root of 2 pi. Now, ladies and gentlemen, let the fun begins. But to just minimize my, not challenge, but, the sign, bring negative 2 out here. So bring negative sign out here. There we go. So the task here is just x times with what? E to the negative what? X squared over 2. There we go, guys. That's it. That is it. Remember, I put red ink because don't forget the negative. I bring it out to make the problems, easy to digest for me right here. Brothers and sisters, here we go. Look at this. Now you only deal with this guy, and this is now the product rule for you. Simply product rule, and we have done that multiple times. So let's do this. Second derivative, negative 1 over this right here, 2 pi. Okay? All right, what do we have here, ladies and gentlemen? What we have over here, remember guys, I simply want you to capture that u and v. And then you do the product rule, which is u prime v plus v prime u. Okay, do that right here. For the sake of space and, really space right here, can I just give you exactly, really, just bring negative in. This is what you have when you do the second derivative. Okay, here we go. This is what you have. A to the negative x squared over 2 time with x squared minus 1. There we go. All right. This is it, guys. This is your second derivative and what that looks like after you simplify your product rule right here. That is u times v, okay, derivative. There we go. And you will have this beautiful formula here. It's not that complicated, but just be careful with the details and the sign. And you get right here. Now look. Now what? How do I show that the function has 2 points of inflections? Can anyone shout out really? Yeah, that's right. You said this what? Equals 0. Thank you. Points to you. Plural, because this is a big problem. Here we go. You see right now, this one can go to, this one, any value for x that make this one 0? Nope, you cannot. Nothing can make this one go to 0 because e to the exponent. Therefore, the only factor that turn the whole function, the second derivative into 0 is x squared minus 1. X squared minus 1. There we go. Now we are close to our solution. X squared minus 1. Solve this for x. What you got? X squared equals 1. And then take square root both sides. Plus it. Boom. We have solved the mystery. Guys, you see that? Okay. There we go. We just hit the nail on its head to point out that the function has 2 points of inflection at the point plus and minus 1. You take second derivative. And once you have the second derivative, what do? You set second derivative equals 0. And then you see that you solve for x. This one, you divide both sides by that, 0 is still gone, time this. And this one, there is no value for x that can make this one into 0. Nope, no value. Therefore, now the second derivative depends on this factor right here. To make that turn into 0, there is there are only two values for x, that is positive, negative 1. This is dealing with second derivative. Therefore, when you have the second derivative equals 0, that guarantees you, not guarantee, but really in this nature particular problem, you can show that I just verify that the function has 2 points of inflection at positive and negative 1. Those are the 2 points right there. Okay, we just dealt with a big potato right there, guys. All right, can I move into integration? Number 6 is just application, and to show you that in your economic function, you can see how the graph looks like, and you plug in the value t. T could be 10 years, 5 years, and normally your economic function looks like an exponential form, and you want to find at that particular year, what would the money look like? Which means you take what? Yep, derivative, the rate of change, which is at that particular year, and you plug in. It's self-explanatory to you on example 6. Can I move into another yummy part, and that is integration for the day? All right, okay, let me pause the video and see you next video.